Welcome back everyone. In this lecture we will see a proof of Freudenthal's formula. So later we will use this formula to prove the wild character formula. So I am actually planning to give a couple of proofs of wild character formula, but only this proof that uses Freudenthal formula will be given in very much detail. All other proof will be outlined. For example, we will talk about BGG resolution and then how to actually get the wild character formula from the BGG resolution, but we will only outline the proof of that using BGG resolution. So, let us first state this Freudenthal's formula, and this actually kind of gives you inductive way to compute the multiplicity of given weight in a given irreducible representation. So, let us first fix some notation and then write down the formula. So, let us recall for SLN. So, given dominant weight lambda, we have this finite dimensional irreducible representation associated with that dominant weight lambda that will be denoted as V lambda. So, given lambda dominant, so recall this V of lambda is the finite dimensional irreducible G module corresponding to that lambda. So, now we are interested in actually computing weight multiplicities of various weights for this finite dimensional irreducible module. So, let us use this notation. So, we know that the action of H is diagonalizable on V. So, we can write it as V as direct sum of V mu, where mu runs over capital lambda. Capital lambda is the weight lattice. So, the dimension of this V mu, that is what we are interested in. So, we will just denote it by m lambda mu. So, m lambda mu defined to be the dimension of these V mu's. So, this is the notation that we are going to use. So, if we use this notation, then the Freudenthal formula is actually gives recursive way of actually computing the weight multiplicity starting from the weight of lambda, which is actually 1, that much we know. So, the m lambda lambda, so which is in some sense the highest weight, and the multiplicity of that. So, that is exactly 1, that is something we know. So, this is the dimension of V lambda, which is spanned by the highest weight vector. So, the highest weight space is spanned by the highest weight vector V lambda. So, that is why it is one dimensional. So, now with this notations, let us write down the formula. The formula looks as follows. So, if you take this m lambda mu, then there is a natural scalar lambda plus rho square minus mu plus rho square times this m lambda mu, which is the multiplicity that we are interested in. So, that is exactly equal to twice summation over alpha in delta plus and then summation over some I range from 1 to infinity, the multiplicity of this mu plus I alpha inside V of lambda times this inner product mu plus I alpha times alpha. So, this is what you get when you actually write down the Freudenthal's formula. So, this formula is indeed very powerful. You can see that the terms that are appearing on the right side, they are actually lies above mu, okay, because it is. So, you have started with mu and then you are adding some I alpha. So, if it is a weight, it must lie bigger than mu, so above mu, and then obviously all the weights are smaller than lambda. So, this is actually going to lie below lambda, and we know that there are only finitely many weights in between these two, and then if we know the information about all the multiplicities that are lying above mu, not including mu, then this formula actually very explicitly gives you the multiplicity of mu in terms of other multiplicities. So, it is not hard to see whenever lambda is different from mu, this term that is there on this left hand side. So, this is non-zero and this term is actually 0 if and only if lambda is mu. So, that actually tells you that you can invert this and then the multiplicity of mu is given by multiplicities of the elements which lie above mu. Okay. And given mu, it will be easy to compute what will be this inner product and so on. So, that way this is actually indeed very powerful formula to compute multiplicity of given weight mu. And of course, what is the idea behind such formula? So, how one can obtain this formula? The key idea is to actually use the Casimir element and then use the action of that on the irreducible representation and then you restrict that action to the weight space and then see what happens to that action. So, basically we will compute the trace of this Casimir element acting on this weight space V mu in two different ways. So, there is a very explicit expression of the Casimir element in terms of the chosen basis of this G. So, once we fix that expression, then we can actually compute how that elements in that expression act on the given weight space V mu. So, that way we can compute the trace in one hand, but we know that the Casimir element that is going to act as a scalar on the irreducible representation V lambda. So, in particularly using that we have already computed how the Casimir element act on that V of lambda via the scalar C lambda. Okay. That C lambda is very explicit. So, now using that two different way of computing trace of this given Casimir operator, then we will be able to actually prove this identity. So, that is the core idea. So, let us actually try to do this very explicitly. So, for that purpose, let us recall how one can define the Casimir element and then I want that very explicit expression of the Casimir element. So, recall, so this is something general discussion that we have already done. So, if you fix a basis, let us say x1 etc. xn, so this is a basis of G and then if you take y1 etc. yn to be the dual basis of G with respect to this x1 etc. xn and the dual with respect to let us say killing form. Okay. So, this is such that the killing form of xi yj is nothing but delta ij. So, we indeed use the trace form for SLN plus 1 in all our calculation, but we also observed that the killing form is just a multiple of trace form. So, one can actually now take the killing form, there is no issue. So, now once we have this basis, then what we proved, so this is something we proved earlier, when you take this product of xi yi where the sum over 1 to n, so this is an element of the universal Olympic algebra. So, we proved that this element is indeed in the center of the universal Olympic algebra. So, this is in the center. So, this is something we have already proved. So, now we are going to, so these elements are called Casimir elements. So, now we are going to actually specifically choose some basis that is coming from the root vectors. Now, using that basis we will actually find the dual basis and then we define the Casimir element that we are interested in. So, let us recall. So, we have the following basis for G. So, G can be written as direct sum of 3 subspaces n plus direct sum H, direct sum n minus. So, H has dimension, the dimension of H is the rank of the Lie algebra which is n. So, we are working G is nothing but SLN plus 1. So, now n plus n minus, we know what are all the ranks. N plus is the upper triangular matrices, n minus is the lower triangular matrices that comes from this SLN plus 1. So, now we are going to use the root vectors. So, we will actually use the induction on the set of positive roots. So, recall delta plus is nothing but the set of positive roots So, now if we use this set of positive roots, then we have the following basis. So, we have a basis h 1 etcetera h n. So, this is the basis of h. Then we have the basis x alpha, alpha in delta plus. So, that is the basis of n plus. Then you have the y alpha, which is the basis of n minus. So, now with these bases we can actually see that it is easy to find the dual basis. So, the corresponding dual basis one can write down, but before that let us actually observe that. So, if you set, for example, it is natural to set this x minus alpha, you can take it to be y alpha, and then y minus alpha you can take it to be x alpha for all alpha in delta plus. So, then with this notation it is not hard to prove the kappa of x alpha y beta is nothing but 0 whenever alpha not equal to beta. So, these things are already done. So, because they are true in the trace form, so they must be true even in the killing form. Now, if you adjust the scalars, then you can easily see that the kappa of x alpha y alpha, so this is going to be 2 divided by alpha alpha. So, one can normalize so that it becomes 1. So, now the kappa of T alpha H alpha, so this is given by alpha of H alpha, which is exactly 2, and this is true for all alpha in delta and for all alpha in again delta. So, this is also alpha beta is in delta. So, with this notation one can rewrite everything very compact way. So, now these things are already known. So, in particularly we know the dual basis of these bases. The dual to h 1 etcetera h n will be just off times T I. So, off time T I is the dual of this. So, basically we are writing dual for everything. So, for x alpha the dual will be y alpha, and for y alpha the dual will be x alpha. So, these are all the dual bases. So, now with this dual let us actually compute what will be the Casimir element. Okay. So, if we rewrite the Casimir element, we can easily see that. So, since this x alpha y alpha can be rewritten as y alpha x alpha plus h alpha, because we want to keep x alpha always on the right side for alpha positive. So, that is why we want to rewrite this. So, since this relation is true, so we can actually see that the Casimir element is nothing but off times summation T I H I ranging from 1 to n. So, note that T I is nothing but T alpha I and H I is nothing but H alpha I. So, these are already used previously. So, this is going to be exactly first summand is off times summation T I H I, and the second summand. So, we will have summation x alpha y alpha, okay, that will correspond to n plus summation x alpha y alpha, alpha in delta plus. So, this corresponds to h, this corresponds to n plus, and then we will have y alpha x alpha, alpha in delta plus, this corresponds to n minus. Now, use this star and then rewrite these things, then you can easily see that this C becomes off times summation T I x I, T I h I range from 1 to n plus. So, this you can rewrite as y alpha x alpha plus h alpha. So, this gives me summation h alpha, alpha in delta plus summation. So, you will add twice y alpha x alpha, alpha in delta plus. So, this is our Casimir element. This is our Casimir element. So, we are going to use this Casimir element to compute how it acts on V mu, and then we will compute the trace of this. Okay. So, to do that, first observe that, okay, let us call this is first summand, this is second summand, and this is third summand. So, since V mu is the muth weight space, so the elements of Cartan subalgebra H will leave it invariant, and here we have y alpha x alpha. So, x alpha is going to map V mu to V mu plus alpha. and then y alpha is going to map v mu plus alpha to v mu. So, if you put them together, you can see that y alpha x alpha is going to map v mu to v mu. So, since this operator maps v mu to v mu, one can actually talk about the trace of this operator acting on v mu. So, each element in this summand, you can see that they all preserve v mu. So, one can compute the trace of C restricted on v mu by computing trace individually for each summand. Okay, that is what we are going to do. So, the trace that we are interested in computing for C restricted v mu, the trace of this is exactly equal to the trace of the first summand restricted to v mu plus the second summand restricted to v mu plus the third one restricted to v mu. So, this is always true, but note that C acts on v of lambda as a scalar which is C lambda. So, which is something we calculated earlier, we will again calculate because we are going to calculate it on any v mu. Okay. So, in particularly one will be able to calculate for this v lambda as well, which is obtained by calculating how this C act on the highest weight vector v lambda. Okay. So, this has some explicit expression, we will actually see what it is. Since it is acting as C lambda, so the trace of C restricted to v mu is going to be exactly C lambda times the multiplicity of mu inside lambda. So, this is something obvious because the Casimir element lies in the center. So, it acts as scalar on the irreducible representation. Since it is scalar times identity, so the trace on v mu is going to be that dimension of that weight space times C lambda. So, that is obvious. So, now we are going to actually calculate what will happen to the first and second and third summands which acting on v mu. So, that is not that hard. So, let us actually first do it for the first one. So, since so for mu in lambda and a vector v in v mu, so we want to calculate how the first summand is acting. So, note that if I take any h in h, hv is going to be mu of hv. So, because v mu by definition, so v mu by definition those w in v such that h w equal to mu of h w for all h in h. So, because of that for any vector v in v mu we have h v equal to mu of h v, and this is true for all h in h. In particularly if you take this summation T I h I acting on v of times this I ranging from 1 to n, you can see that this is exactly is going to be of times summation mu of h I times mu of T I ranging from 1 to n acting on this vector v. Okay. So, but it is not hard to see the summation mu of h I times mu of T I, because mu I and h I and T I they are dual bases with respect to the Killing form. So, if you use that information, then you can easily see that this is exactly equal to the inner product mu mu. Okay. So, this is something we have already done. Anyway, I will leave it as exercise for you to do it again. So, now this actually says if you take this operator of times summation T I h I, so that is going to act as the scalar mu mu on this entire space v mu. So, in particularly what will be the trace of that? So, the trace of this operator of times summation T I h I ranging from 1 to n restricted on v mu. So, this is going to be exactly the mu mu times the multiplicity of mu in v lambda. So, which is the dimension of that space v mu. So, this is exactly the first summand actually gives you the trace. So, now let us look at the second one. So, this is let us call it lemma 2. So, if you take the second one again for mu in lambda and then the vector v in v mu, you can see that the summation H alpha alpha in delta plus. So, how it acts on V. So, this is going to be, because H alpha is going to act as mu of H alpha. So, this is going to be summation mu of H alpha times V alpha runs over delta plus. Now, we already know that what is mu of H alpha. Mu of H alpha is nothing but twice mu alpha divided by alpha alpha, because we are in type A, alpha alpha is 2. So, this is exactly mu alpha. So, this is what you get it on the right side. So, then that means summation H alpha alpha in delta plus acts on this V as. So, if you run it over summation alpha and delta plus, you can easily see that this is exactly mu times 2 rho acting on V, because sum over this mu of H alpha is going to be sum over mu alpha. So, since this is a bilinear form, so you can take the summation inside, then that summation alpha alpha and delta plus is nothing but twice times rho. So, that gives you that the trace of. So, this gives me that trace of summation H alpha alpha in delta plus. So, when you restrict on this V mu, so this is exactly equal to mu times 2. So, the inner product mu comma 2 rho times the multiplicity of this mu inside V of lambda. So, this is our second summand. So, that is exactly giving you this mu comma 2 rho times this multiplicity. So, now let us look at the third summand. So, the third summand is bit tricky. So, that we uses what is called this SL2 representation theory. So, let us actually do this third summand slowly. So, as an aside, let us recall some of the things that we needed from the SL2 representation theory. So, if we take V of m to be the irreducible representation, irreducible finite dimensional SL2 representation, then we know that we have this basis V0, V1, etc., Vm. So, this is the special basis that we have for this irreducible representation, on which we know how this H acts. H of Vi is going to be m minus 2i times Vi. So, this is something very explicit. Similarly, yVi is going to be I plus 1 times Vi. So, now how this xVi x acts on Vi, xVi is going to be m minus I plus 1 times V, sorry, this is I plus 1, this is I minus 1. So, y actually increases Vi to Vi plus 1, and then x actually decreases Vi to Vi minus 1. So, this is something very explicit. This is something we have done it using SL2 representation theory. Now, if we use these formulas, one can actually compute how the trace of y alpha x alpha will be on this V mu. Okay. So, let us do this for alpha again in delta plus and mu in lambda. So, if we compute the trace, so the trace of y alpha x alpha acting on this V mu. So, this is exactly given by twice. So, we can actually forget the 2. So, this is exactly summation m range from I range from 1 to infinity m of mu plus I alpha lambda mu plus I alpha times alpha. So, this is how the trace of y alpha x alpha looks like when you restrict this operator on V mu. So, note that this is what you have it in the Freudenthal formula. Okay. So, if you go back to the formula, you can see such term appearing in the Freudenthal formula. So, that is the motivation for these formulas. Okay. So, here you can see that it is appearing here. Okay. So, let us actually prove that, and then we will have the proof of Freudenthal formula immediately. Okay. How one can actually prove this? So, let us actually try to understand this. So, for this purpose, first we need to actually construct some SL2 sub representation. So, because this you can see that the weights actually run through mu plus I alpha, I ranging from 1 to infinity. So, because of that you can actually to be on safe side, because SL2 invariant means it should be that operator S alpha invariant, S alpha is being the reflection. So, for that purpose what we are going to do, we are going to construct this interesting space, let us call it W bar. So, which is direct sum of all these weight spaces mu plus I alpha, I runs over all integers. So, this is going to be a subspace of V. So, one can easily see that. So, this is indeed SL2 alpha invariant subspace. So, this is a finite dimensional SL2 alpha. So, SL2 copy is nothing but the C span of all this X alpha, H alpha and Y alpha. So, this is the SL2 alpha of copy. Then this W bar is a finite dimensional SL2 alpha submodule of V lambda. So, now since this is finite dimensional module, because V of lambda itself is a finite dimensional module. So, using the complete reducibility, one can actually decompose this W bar into some direct sum of irreducible representations of these SL2. So, this is the direct sum of SL2 alpha irreducible representations. So, once we have this, now it is easy to see how one can compute this trace of this Y alpha X alpha by restricting to this W bar. So, it is not hard to see the W bar muth weight space is going to be just exactly the muth weight space of V, okay, because so basically we have taken the direct sum of mu plus I alpha weight spaces. So, when you restrict this W bar to the muth weight space, you will get exactly V muth weight space. Then that is going to be exactly equal to U1 mu direct sum etc. direct sum U D mu. So, we have that W bar is equal to the direct sum of these UIs. In particularly, if you look at this muth weight space of W bar, so that is going to be exactly V mu, which is nothing but the muth weight space of each U of I. So, now if you are interested in calculating this trace of this Y alpha X alpha acting on this V mu. So, this is same as calculating the trace on this W bar mu. So, which is exactly equal to the sum of the individual traces, the trace of Y alpha X alpha acting on this U I mu for I ranging from 1 to D. So, now for this purpose we actually assume that we are actually calculating the trace on this U I mu. So, let us start with some element there and then try to compute the trace of this. So, note that if I start with the vector V, so which is inside let us say U I of mu. Okay. So, we just assume that this space is being non-zero. So, we want to actually calculate how this Y alpha X alpha act on this space. So, now so we have two cases for the possibility of mu of H alpha. So, let us first consider this case 1. The case 1 is mu of H alpha is being non-negative. The case mu of H alpha being non-positive, that is also similarly done, that I will leave it as exercise. We will only focus on this case mu of H alpha being non-negative. So, now in this situation we want to compute how Y alpha X alpha acts on this V. Okay. For that purpose we will actually switch, because this V is inside some weight space mu. So, in particularly the SL2 alpha weight or H alpha weight is mu of H alpha. Okay. So, the mu has weight mu of H alpha as H alpha weight. So, this may not be actually the highest weight. So, we will actually switch the weight to the highest weight. For that purpose, let us start with the maximal element. Okay. Choose k being maximal such that this u I mu plus k alpha is non-zero. So, such maximal exists because we are all working in the 5 dimensional spaces. Okay. So, we can't keep on adding this multiple of alpha. So, we have to stop at some point. You choose k maximal such that this is being non-zero. Then it is clear that this ui has the highest weight mu of H alpha plus 2k, which is nothing but mu plus k alpha of H alpha. So, in particularly this irreducible component ui is actually isomorphic to the highest weight representation corresponding to this mu of H alpha plus 2k. So, now, so what is this muth weight space corresponds to? That corresponds to the weight mu of H alpha. So, now go back to the SL2 representation theory, then you can easily see that if you have this V of m irreducible representation corresponding to the non-negative integer m, then we have the basis V naught, V1 etc. Vm. So, on which H acts as m minus 2i Vi. So, in particularly this is the weight m minus 2i, weight of this Vi, and x acts as m minus I plus 1 times Vi minus 1, and y acts as I plus 1 times Vi plus 1. So, in particularly yx acting on Vi will be exactly m minus I plus 1 Vi minus 1 on which y acts. So, it gives I times this m minus I plus 1 Vi. So, this is the action on this ith element Vi, which corresponds to the weight m minus 2i. So, if we do the similar thing here, so we have m to be mu of H alpha plus 2k, which is the highest weight, and this m minus 2i being the weight mu of H alpha. So, that is what corresponds to the vector chosen vector V inside this ui mu. So, this m minus 2i is nothing but mu of H alpha. Now, if you do the calculation, you can easily see that mu of H alpha plus 2k minus 2i is nothing but mu of H alpha. So, that forces k being equal to I. So, in particularly this Vi corresponds to V. So, if I take this y alpha x alpha acting on this V, it is same as this y x acting on Vi, which is giving us, so I is equal to k. So, we can call it k. Then this y alpha x alpha acting on this V exactly give us k times m is nothing but mu of H alpha plus 2k. So, mu of H alpha plus 2k minus k plus 1 on this Vk. So, that is what you are getting on this vector V. So, in particularly you can see that y alpha x alpha V is nothing but k times mu of H alpha plus k plus 1 times V. So, this is what we are getting on this ui mu. Okay. But note that the multiplicity of Vi, that is the dimension of that space, is 1 inside V of m. So, u of I being isomorphic to Vm. So, ui mu will be exactly spanned by this Vi. Okay. So, this is one dimensional. So, the trace of this is going to be on this space exactly k times mu of H alpha plus k plus 1. So, the trace of this y alpha x alpha restricted to this ui mu is exactly equal to k times mu of h alpha plus k plus 1. So, that is what you get by calculating the trace on this. So, now how do you put it back to compute the trace on V mu? So, that is something one can obtain from this equality. So, here if you are interested in computing the trace of y alpha x alpha acting on V mu, then we have to calculate the number of times ui that appears in the summand. Okay, that is ui means ui being isomorphic to, let us say, V of m. So, how many times V m appears there inside this direct sum. So, that is going to give you exact the multiplicity of that thing. Okay. So, it is not hard to see that the number of summands ui which are isomorphic to so this V of mu plus h alpha plus 2k. So, that is the weight, highest weight that we are talking about. So, that is the m that we have. So, that is going to be exactly given by, so this is one can calculate. So, this can be calculated using the multiplicity of this mu of h alpha plus 2k and the multiplicity of mu of h alpha plus 2k plus 1. So, that is going to be exactly, you look at the W bar and look at the multiplicity of mu of h alpha plus 2k and then you subtract this with the multiplicity of W bar mu of h alpha plus 2 times k plus 1. Okay. So, this is something we have actually done it for any finite dimensional representation. So, if given V m, if you want to compute the multiplicity of V m in a given representation, let us say W, then look at the dimension of W m minus dimension of W m plus 2. So, that is going to give you the number of summands. So, because this is what gives you the number of summands, now it is easy to compute the trace of this y alpha x alpha on V mu. So, that is going to be the sum of the traces which is given by this multiplicity times the individual trace. So, this is exactly the summation runs over k from 0 to infinity, this multiplicity of this summands. So, which is again given by just you take the multiplicity of mu plus k alpha inside lambda, inside this V of lambda, minus the multiplicity of mu plus k plus 1 alpha inside V lambda. Because that is going to be the exactly the multiplicity of this mu of h alpha plus 2k. Because W bar is nothing but the direct sum of the weight spaces corresponding to mu plus I alpha. When you evaluate on h alpha, it is going to give you mu of h alpha plus 2i 2i. So, for various I, they are all will be distinct. So, then that implies that exactly the multiplicity of mu of h alpha plus 2k will be the multiplicity of this mu plus k alpha inside V lambda, which is the dimension of this V mu plus k alpha. Okay. This similar arguments we have given many times. So, the same argument works here, and that actually tells you that if you are interested in computing this trace of y alpha x alpha on V mu, that is going to be exactly this multiplicity times this trace k times mu of h alpha plus k plus 1. So, this is exactly multiplicity mu plus k alpha lambda minus multiplicity mu plus k plus 1 alpha lambda times this k times mu of h alpha plus k plus 1. So, this is what our trace of y alpha x alpha when we restrict on V b. Now, the case mu of h alpha being less than or equal to 0 can be handled similarly. Maybe I will leave it as exercise. So, when mu of h alpha is less than or equal to 0, so now instead of working with the highest weight, one can work with the lowest weight vectors, and similar calculation shows that shows that we have the following formula. The trace of x y alpha x alpha on V mu is going to be minus of summation the multiplicity. Okay. So, actually let us simplify this, and then we can rewrite as follows. Okay. So, if you rewrite this, you can easily see that this is exactly equal to summation m k equal to 1 to infinity the multiplicity of mu plus k alpha lambda times mu of h alpha plus 2k. Okay. So, this is not very hard to see. Let me leave it as exercise. So, this is just exercise. Rewrite this, you get this. So, using that, so if you actually compute it for mu of h alpha less than or equal to 0, then you get similar formula. So, the similar formula will look like multiplicity of mu minus k alpha inside V lambda, where k runs over 0 to infinity, times mu of h alpha minus 2k. So, this is what you get for mu of h alpha less than or equal to 0. So, now if you put them together, what do you get? Okay. So, before that we want to rewrite this again, this double star. So, how do you rewrite? One can rewrite this using this h alpha, action of h alpha. So, note that h alpha is nothing but the commutator of x alpha y alpha. So, which is nothing but x alpha y alpha minus y alpha x alpha. So, now we know how h alpha acts on the individual weight spaces. So, it is easy to see that the trace of h alpha restricted on V mu. So, that is supposed to be 0, because that is exactly the commutator of this x alpha y alpha. So, the trace of the commutator is going to be 0. So, this is going to give us, okay. So, if I take this trace of h alpha, so one can actually compute it on w mu bar. So, this is same as trace of h alpha on w mu bar, but w mu bar. So, note that w is nothing but direct sum of v w bar is nothing but direct sum of v mu plus I alpha. I varies over integers. So, because of that, you can see that if you are interested in computing this h alpha on each weight spaces, it is going to act as mu of h alpha plus 2I. So, now you have to sum over all of them. So, this is going to be summation minus infinity to infinity the multiplicity of this mu plus I alpha lambda, and then mu plus I alpha applied on this h alpha. So, that is going to be your trace. So, if you rewrite this, then you can see that this is exactly equal to summation minus infinity to infinity the multiplicity of mu plus I alpha lambda mu of h alpha plus 2I, and this is exactly 0. So, if you keep this summation 1 to infinity here, where let us say k range from 1 to infinity, then this is going to be multiplicity of mu plus k alpha lambda mu of h alpha plus 2k. So, this is exactly equal to minus summation 0 to infinity, where let us say b equal to 0 to infinity the multiplicity of lambda mu minus b alpha mu of h alpha minus twice b. So, that is what you get. Now, this is the term that you are actually getting it here in this double star. Okay. So, now because of that you can replace the double star by this term, which is exactly what we wanted in the first place. Okay. So, this says that this trace of y alpha x alpha on this V mu, even in this case when mu of h alpha is less than or equal to 0, we get the same formula, trace of y alpha x alpha on this V mu even in the case mu of H alpha less than or equal to 0 is going to be exactly equal to multiplicity of this mu plus k alpha, mu of H alpha plus 2k, where k ranging from 1 to infinity. Okay. So, this is what we get at the end. So, now we can put everything together and then we can see that we get what we wanted. Okay. But before that let us see actually what we get when we apply it on the highest weight. So, now so let us recall. Okay. So, what we have done so far. So, we had 3 summands and each summand actually gives you something. So, summation H alpha alpha in delta plus. So, that is giving you mu 2 rho multiplicity lambda mu, and then summation T I H I ranging from 1 to n of times. Okay. So, this is gives us mu mu times m mu lambda. Now, by computing this twice summation y alpha x alpha alpha in delta plus. So, this gives us exactly twice summation alpha in delta plus summation m ranging from 1 to infinity multiplicity of mu plus m alpha lambda mu m alpha alpha. So, this is what it gives, because this mu of H alpha 2 k can be written as mu plus k alpha of H alpha. So, which is same as mu plus k alpha alpha. So, this is what we get at the end. Now, if we take the trace on the both side of the Casimir operator, then you can easily see that we get exactly C lambda, the multiplicity of mu, which is exactly equal to mu comma 2 rho, the multiplicity of lambda plus mu mu, the multiplicity of mu, plus twice summation alpha in delta plus summation m ranging from 1 to infinity, the multiplicity, maybe I will write I, mu plus I alpha lambda mu plus I alpha alpha. So, this is what we get. So, now this same calculation can be done for mu equal to lambda. When you take mu equal to lambda, you know that the multiplicity of lambda is 1 and this x alpha is going to act as 0 on V lambda. So, V lambda is inside this V lambda, which is the one dimensional space. Now, using that you can see that, or even in this summation. So, if mu is the highest weight, then mu plus I alpha cannot be a weight. So, then these multiplicities will become 0. So, that actually tells you that C lambda is nothing but lambda comma 2 rho plus lambda comma lambda. But it is not hard to see for any mu. So, mu comma 2 rho plus mu comma mu. So, this is exactly equal to the norm of mu plus rho square minus the norm of rho square. So, this is true for any mu in lambda. So, I will leave it as exercise, this is not very hard. So, if you take any mu coming from lambda, the inner product that we have in the summations mu comma 2 rho plus mu mu, that is nothing but the difference between this mu plus rho square minus rho square. So, now if you use that, then this actually becomes the norm of lambda plus rho square minus norm of rho square. So, now if you put back in this equation, you can easily see that. So, because this m lambda mu and m lambda mu is here, so it will become the difference. So, then this is exactly equal to m mu lambda. So, which is C lambda minus mu comma 2 rho minus mu mu is going to be the exactly equal to norm of lambda plus rho square minus norm of mu plus rho square times m mu lambda. So, this will be on the left hand side, and right hand side as it is. So, this one twice summation alpha in delta plus summation m mu multiplicity of mu plus I alpha times mu plus I alpha comma alpha. So, putting them together we get the Freudenthal formula. So, this is the final formula, the norm of lambda plus rho square minus norm of mu plus rho square times the multiplicity of mu inside this V lambda is equal to twice summation alpha in delta plus summation I range from 1 to infinity the multiplicity of mu plus I alpha times the inner product mu plus I alpha comma alpha. So, this is the final formula that we get by comparing the trace of the Casimir operators in two different ways. So, this indeed completes the proof. So, we will use this proof in order to actually prove this this wild character formula. So, this is actually the simplest proof one can actually expect. So, there are more involved proofs using the representation theory, okay, that maybe I will outline. So, I will stop here. We will continue with the wild character formula in the next class. Thank you.